Okay, great. Then let's continue with Remi Coulon's third talk on twisted Patterson-Sullivan measures. Okay, all yours,
Yeah,
Remi.
thank you
Thanks.
very much. Yeah, just before I start, someone asked me the following question yesterday, which was if you have a collection of density, Patterson-Sullivan density. So imagine now what you have a point x, well, a sequence xn that converges to a certain point in the boundary at infinity. What can you say about the sequence of measure here? Does it converge to something? And so, if I'm not mistaken, if you do the computation, just writing, the densities, you'll see that you converge to a measure which is fully supported on that point at infinity. Maybe it's not a finite measure; it can have an infinite mass, but the support is exactly that point here. So that was to answer the question.
Thank you. Yes.
I skipped yesterday. So that you can write down everything explicitly normally. Okay, so let's go back to the statement I intend to prove. So for the moment, I have given you a simplified statement, which is the first one that appears on the screen right now. So which is you consider group G, a subgroup, which is normal subgroup N, and you compare the growth rate of those two groups, and you say they are the same if the quotient is amenable. And this was under the assumption that the group G acts properly, co-compactly on a hyperbolic space. So actually, a much weaker assumption is enough to let the same kind of proof and result holds. And this is a full theorem that I studied now on the board and that I want to discuss and eventually prove. So I highlighted the main differences. So we start still with the group G, which acts by symmetry on a hyperbolic space. But now, instead of asking that the action is co-compact, we ask that it is strongly positively recurrent. I will give you the definition right after so that you see what it is. But that's a weakening of the co-compactness assumption. So that's the first weakening we can do. And the second one is on the subgroup N. So now I'm no more asking that H is a normal subgroup. I will consider any subgroup H in G. So the conclusion will be, well, the two growth rates are the same. This does not change. If and only if. So I want to say the quotient G mod H is amenable, but I cannot exactly say that because H is not a normal subgroup. So the proper way to say that is that H is co-amenable in G. And then let me start right now by giving you the definition of co-amenability. So as for amenability, there are hundreds of possible definitions. So I listed 3 of them. And if you know the proof to go from one to the other, in the case of standard amenable groups, you will be able to just take those proofs and write them again to get the equivalence between the 3 properties. So first definition, the one which makes sense if you think of a mean. So H is co-amenable in G if there is an invariant mean on the set of bounded function of G mod H. So G acts by translation on G mod H, so that induces an action of G on the set of bounded function on G mod H. And then you ask that there is a mean which is invariant for this action. So first possible definition. During the first lecture, I gave you another definition of amenability using almost invariant vectors. So here is the analog. So again, G acts by translation on the coset G mod H, so that induces a unitary representation from G into unitary operators on this Hilbert space here, L2 of G mod H. And then the H is co-amenable in G if and only if that representation almost has invariant vectors. So you have vectors which, if you fix a finite subset and a small epsilon, they are hardly moved, hardly means by at most epsilon, by any element in this subset, in the finite subset you fixed. And the last definition possible is that the Schreier graph of G mod H is immutable, so which means that its Chigger constants is 0. So let's have some examples. So the first one is, what does this definition tells you if N is actually a normal subgroup? And if N is a normal subgroup, it's very easy to check that N is co-immutable in G if and only if G mod N is immutable. So we're safe. We're just extending the notion of amenability for quotients which are not really groups, but just Schreier graph or coset spaces. So another more maybe interesting examples is, so I start with the group G, and I will consider the subgroup H, which is generated by all the conjugate of B by a positive power of A. And I claim that H is commutable in G. So H commutable in G. So how can we say that, see that? Well, probably the best way is to start drawing the Kelly graph of G, which is the free groups, this is standard for regular tree. So let me use some color. So let's say this is the generator A, and this is the generator B. And now I want to draw the Kelly graph, well, the Schreier graph of G mod H. So what's happening if you take, for instance, let me use some color. If you look at that line here, this line will be the axis of AB A inverse. So if I quotient by AB A inverse, I will collapse that line. And not only I collapse this vertical red line, but you will identify this orange line with this line here, something like that. So, and you do that for all, all possible translate, the positive translate of the axis of B. So you are collecting vertically a lot of branches in your Kelly graph. So at the end, what you will get is, well, there is one part of the Kelly graph that is not changed. So the left part of your Kelly graph, the upper part and right part does not change. But here you have just a bunch of loops because you still need to have a regular graph that goes to infinity. And these, so that's infinite. But now the observation is that this part here, essentially that's a line. So in a line, you can find arbitrary large set whose boundary is finite. So that will give you a Chigger constant which is 0. So therefore, the quotient G mod H, well, is amenable, or more precisely, H is co-amenable in G. Does that make sense? Well, I guess so. So that's a possible example of a group which is co-amenable in G, but which is not a normal subgroup. Okay, so now let's move to the other assumption I weakened, which is strong positive recurrence. So basically, let's start from the situation we understand quite well in general. So this situation is what's called convex concompact. So what does it mean? It means that in your space, so you have your space X you're acting on. And in this space, there is a certain quasi-convex subset that we write like this. So a quasi-subset Y, such that the action of G on this subset will preserve this convex Y. And not only it preserves it, but it acts properly concompactly when you restrict the action of G to Y. So somehow, a quasi-convex subset of a hyperbolic space is still a hyperbolic space. So it's exactly like you were handling a proper compact action. So this kind of situation has been studied for a very long time, and that's a situation we understand quite well. So now what we'd like to understand is, what if the action is no more convex compact? So meaning that somehow the orbit of the group G is not convex. And how much this action then is not convex. And that's the purpose of strongly positive recurrence. So
I have a question.
Sure.
In your earlier example, could you go back to that example?
Yes.
Yeah. So what is the picture on the right? This is the picture for the paragraph. Or?
That's supposed to be the Schreier graph of
yeah. But is that not? But does that not just have one loop? I mean, the Schreier graph that corresponds to the covering space of corresponding to H, right? For
I made a mistake. Maybe I made a mistake. Why would there be just one loop?
I mean, so for the covering space corresponding to the, so the Schreier graph of G by H is the covering space corresponding to H of the wedge of two circles, right? But that just has one loop, I think, right? Because that's the fundamental group of that is H.
But H is infinitely generated. H is
yeah, but
by all the conjugate of B.
Yeah, that's the normal. That's the normal closure of a cyclic.
No, it's
group,
not.
Right?
It's not.
No, it's not the normal.
It's not the normal closure, because you take the conjugate only by positive powers of A.
Ah, I see. Okay. Okay. Yeah, I got it.
That's the point. So if I had taken the normal closure, then it would have been a normal subgroup. It is not something I want. So I only take the
yeah, okay,
subgroup generating by the positive power of A. Well, B conjugated by positive power of A. Does that make sense?
Okay.
Maybe a quick comment to clarify. I guess you mean that there will be larger and larger pieces which look amenable, right? That's the criterion where you say that the Cheever constant is 0.
Yes, exactly. So it means that in the trigraph, you may have parts which looks like a tree. That's not a contradiction with being amenable for a graph, because what matters is that somewhere else there are portions of graphs which looks more and more amenable. Does that make sense?
Yeah, thank you.
Good. So don't hesitate to stop me anytime if there is something which is not clear. Okay, so let me move back to strongly positively recurrent actions. So as I said, what I want to understand is why the action of G on the space X is not convex, and how can I measure that? So let me introduce a certain set that may look weird at first, but I'll explain what the idea. So I take a compact subset K here, and I will look at elements in the group that will translate my compact. Here is GK, and for which, if I look at a geodesic from K to GK, so that the geodesic here from X to GY with X and Y in GK, this geodesic will not intersect any other translate of the compact K beside K and the translate by GK. So this is the definition of this somehow weird set. So why is it a relevant set to look at? The idea that if your action is, let's say, proper compact, then for some K, all the G translate of K will cover your space. But if your action is not proper compact, so you will have translates of K, so those are translates of K. But the union of those translate, if the action is not convex and compact, this union will not be a convex subset. So if the union is not a convex subset, it means that you have some geodesic that will violate the convexity or quasi-convexity in the context of hyperbolic spaces. So having something that violates the quasi-convexity means you have a geodesic that will escape those convex. And no matter how big your compact is, you will have a geodesic that escapes the orbits of those compacts. So some geodesic may do something like this. It travel outside, then inside, then outside. That's possible. But then we will only look at the one which start somewhere in this union of compact, escape this union of compact, and come back in a different compact without intersecting any other thing on the way. So that's why somehow those elements that this set of elements that I defined here, they are exactly the elements in G which somehow are responsible for the lack of convexity of the orbit of G. So this is the idea of that set. Okay, and what I say, I want to measure how bad the action is not convex or compact. So what we can do is, well,
question.
Yes.
Is it possible to take y equal to x? I mean, choose this point. Why are x and y different? Is there a reason?
So it's just some matter of comfort when you write the proofs, because since since everything is is not very sensitive to a compact set or bounded set, because when you do all the counting, those kind of errors will give you multiplicative errors in the counting, and then when you take the exponential growth rate, everything will disappear.
Okay, thank you.
So you could have taken x on the both sides, but just is more comfortable to manipulate in this way. Does that answer your question?
Yeah, thank you.
Yeah, so I said I want to measure how bad my action is not convex or compact. So once you have this set gk for certain k, well, you can compute what is the exponential growth rate of the set. So I gave you originally the definition of the exponential growth rate for a group acting on space. But you copy the same definition, and you will get also the exponential growth rate of any particular subset of this group. It does not have necessarily to be a group. So that's why I can define what is exponential growth rate, which somehow tells of this set gk, which somehow tells me asymptotically how many bad elements do we have. And then one defines the entropy at infinity to be the infimum of all possible compact subsets of this growth rate of gk. So that's the measurement of how bad the action is not convex or compact. So it's not very difficult to see that this number, this entropy at infinity, is always bounded above by the growth rate of the group G. And then the definition now is that the action of G on X is strongly positively recurrent if actually the entropy at infinity is strictly less than the growth rate of the ambient group. So it's really saying that from a statistical point of view, of those bad elements which violate the fact that the action is convex or compact, they are in a negligible quantity compared to how many elements you have in the group. So that's exactly the meaning of the strongly positive recurrent definition. So actually it was introduced independently by two teams. One was Shapira and Tapi, that were inspired more by dynamical analogs when you study subsheets of finite types or those kind of things. And on the other side, it was also introduced by Young, which called it statistically convex co-compact. So which is more in the spirit of what I explained to you. This is just telling you that statistically, your action looks like an action which is convex co-compact. Any questions so far? Okay, so if not, maybe let me give you some example of strongly positively recurrent actions. So the first one is you take an action which is proper concompact, or more generally convex compact. You want this to be strongly positively recurrent. So it's not very difficult to show that in this particular case, oops, it's not what I want to do, that's what I want. In this particular case, there exists a certain compact such that GK is finite. So you can prove that. And if GK is finite, then the entropy at infinity is 0. So if your group G is not elementary, then the action is strongly positively recurrent. So now you also have the case of relatively hyperbolic groups. So when you have a group G, which is hyperbolic relative to some parabolics P1, Pm, you may consider an action which is now suitable to that peripheral structure, so which is what I call a cusp-uniform action. I want a yellow one. Cusp-uniform action. So let me briefly tell you what it is with a picture. So basically, you have your hyperbolic space X on which the group G is acting. And then in that space, you have a family of horribles, so which are, well, the family is invariant under the action of G. So that means there would be, if you translate, you would have some stuff like that, etc., etc. And the stabilizer of those horribles up to conjugacy, if they are in one-to-one correspondence with the parabolic Pi, first condition. And the second condition is that if you look at the action on the complement of your horribles, the action on the complement is proper. So this is what I call the cusp-uniform action. Actually, having such an action is a possible definition for relatively hyperbolic groups. So typically, this action is not co-compact because you have parabolics here. But then it's not very difficult to see that the entropy at infinity is, oh, sorry, I did a mistake. That's a mistake. It's not the mean. That's the max of the entropy, of the growth rate of all parabolic subgroups. So basically, if you fix since the action in the complement is proper compact in the complement of the horribles, since the action in the complement in the horribles is co-compact, then you can find a certain compact K that whose orbit will cover the whole complement, right? And now if you think of the definition of those set GK, you're looking at elements that go from this orbit and escape the orbit and come back to the orbit. So roughly speaking, those elements will be parabolic elements. And if you do the counting carefully, you'll see that the entropy at infinity is exactly the maximal growth rate of any parabolic. So in particular, the action will be strongly positively recurrent if the growth rate of every parabolic is strictly smaller than the growth rate of the ambit group. And if you're familiar with the work of Dalbo, Peña, Sambucetti, and all those kind of people, when they work with relatively hyperbolic group, they have a condition they use very often, which is called a growth gap, parabolic growth gap, which is exactly saying that the growth rate of the parabolics is strictly smaller than the growth rate of the ambit group. The strongly positively recurrent action also generalize that setting, that framework. And another example, which now are no more finitely generated group, are Ankona type surface. So let me do a picture. Imagine you take somehow a tree of pens, so something like that. So you have a a pair of pens, and then you attach to it another pens, and again you attach to it another pens. So you do a tree structure like this. Same here, so that will look like this. And you do this in such a way that when you attach your pens, all the curves that I draw in red, you make sure that they have length 1. So those curves here. So of course it continues forever. So those red curves have length 1. And then you also fix the curve here, the 3, 1, around a central pair of pens, and you say that you fix them to have length 1, length x epsilon. So that's a certain manifold. So you take for G the fundamental group of this manifold, which acts on the universal cover, and well, which is negatively curved. And it turns out that if you keep all the red curve to have length 1, and the blue curve to have length epsilon with epsilon sufficiently small, then the action of G on the universal cover, sorry, I wrote that in a bad way. So the action of G on the universal cover is strongly positively recurrent. But since this time, since you have made a tree of pens, the group G itself is not finitely generated. But we don't care here. The important fact is that the action of G on the universal cover is proper, so that we can do counting. We don't need the group to be finitely generated. So, and that's an example which does not come from another setting that was studied before somehow. So that's the meaning of strongly positively recurrent. And well, I titled my lecture today the optimal statement. So I want to argue why I think this is an optimal statement, or at least in the setting of negative curvature. So I remind you what the main theorem is. So you have this group G acting on a hyperbolic space, and you look at the subgroup and say the growth rate are the same of H and G if and only if H is commutable in G. And so we have two big assumptions. The first one is that the group has some kind of negative curvature. It acts on a Gromov hyperbolic space. And second, we have a weak convexity assumption. So we assume that the action of G on X is strongly positively recurrent. These are the two main assumptions of our theorem. And I claim that you cannot weaken one of the other without finding a counterexample. So I want to discuss those counterexamples now. So first, why do we need some kind of negative curvature? Well, imagine you take G, which is a solvable group. So take your favorite solvable group. For instance, if I take G, which is a Baum-Sachs solitary group BS1N. So, and you let it act on its scalar graph, for instance. Well, since the group is solvable, you know that the growth rate of G is positive. But now G is amenable because it's solvable. So now take for H simply the trivial subgroup. So the growth rate of H now will be 0. Although G mod H is amenable. So we have a situation where G mod H is amenable. However, I didn't write it. However, the growth rate of G and the growth rate of H are not the same. So just a way to say that somehow we need somewhere a kind of negative curvature, because otherwise we're doomed. There is no way we can have a statement of this kind. So second assumption, that's strongly positively recurrent action. So I claim also that we need to have a strongly positively recurrent action, otherwise we will find counterexamples. So let me give you my favorite counterexample. So there is a construction which is due to Dalbo, Peña, Sambucetti, if I remember well. Probably Dalbo, Peña, Pico, Sambucetti, I think. So basically, they build a group G, which is the fundamental group of a certain surface, finite volume surface, such that there exists a parabolic subgroup with the same growth rate as the growth rate of the ambit group, and X being here the universal cover of my surface. So typically that's an action which will not be strongly positively recurrent, as we saw previously. G is hyperbolic relative to its the stabilizer of the cusps, and if one of these cusp stabilizer, the parabolic, has the same growth rate than the one of G, the action is not strongly positively recurrent. So what can we do in this situation? Well, basically there is a very nice construction called den filling that you can use to do something fancy. Maybe I should just add another page, because otherwise. Okay, sorry, I'm gonna restart my software because it seems to be picky right now. Okay, so so I have this group G, which is the fundamental group of a surface with a certain parabolic. So again, I have the group G, which is the fundamental group of a certain surface, and there is a parabolic subgroup which has the same exponential growth rate as the one of the ambit group. So now if I make a very rough picture, imagine you have just a surface with one cusp. So what I can do a den filling, which means I'm going to chop off the cusp. So I cut off that stuff. So yeah, I'm not very good today with my software. So basically you get a surface with a boundary, and then instead you attach on it a disk on the boundary, but by wrapping it n times. So you wrap the boundary of the disk n times around the surface. And what you get will be an orbifold with negative curvature, but now which is compact. And if you think in terms of fundamental group, what we have built is we have considered the group G bar, which is the quotient of G by the normal closure of a certain group P naught which is a finite index subgroup. Finite index subgroup of G. And it turned out that this group is Gromov hyperbolic. The reason is the picture I made. So when you cut off the cusp and you attach this disk, if you wrap the disk sufficiently many times around the boundary curve, then you can put a hyperbolic structure on this as this orbifold. And because you have a compact orbifold, then the fundamental group has to be a hyperbolic group. But since this is Gromov hyperbolic, this group is definitely non-amenable. So I have a quotient which is non-amenable. Now, if I write n for this normal closure, let me estimate the growth rate of n. So the growth rate of n, well, this is at least the growth rate of P naught, because P naught is contained in n. But now P naught is a finite index subgroup of my parabolic P. So that's the same as the growth rate of P. Growth rate is not sensitive to finite index. But according to my initial assumption, here, the growth rate of P is the same as the growth rate of G. So this is also the growth rate of G. So which means now I have an example where the growth rate of G and the growth rate of N are the same. However, the quotient is non-amenable. So that's also a counterexample to my theorem. So that means that we cannot drop the assumption that the action is strongly positively recurrent. Does that make sense?
Yep.
Good. So the next and last thing I want to do before moving to the proof is push a bit further the kind of statement that we have. So, our statement basically tells you when a subgroup H has the same growth rate as the ambiguous group G. But now you can ask, well, we know what the maximal growth rate for a subgroup is. Is there a possible gap now between this maximal value and the other possible values? So to speak about the result, I need to use group which has the so-called Gaussian property T. So in terms of representation, it means that anytime you have a representation in a Hilbert space which almost has invariant vector, then it has a non-zero invariant vector. If you're not familiar with this property, I'm not going to use it very much. So let me just give you some examples to keep in mind. So example would be if you take gamma, which is a lattice in SPN1, that's a typical example of a group with property T. Or if you take a random group, so according to Gromov density model, so with large density, I don't remember what is the threshold, maybe 1/3?
1/3, yeah.
Okay, so large density means bigger than 1/3. So if you take a random group with density more than 1/3, this will be also a group with property T. So that's the two examples I have in mind, because that also example we have some kind of negative curvature. There are other examples, like if you take SNNZ for n larger than 3, this will also be an example, but now this is not a rank 1 group, so this is not as relevant for the topic of my talk. And so now, as I told you, the original goal is to describe the possible values of the growth rate of subgroups of G. And the statement we can prove is the following. So imagine now you have a group with property T, which is somehow a rigidity property. So it's not surprising that we use property T to get some growth gap. So if you have group G with property T still acting on the graph hyperbolic space with an action which is strongly positively recurrent, so then you can find an epsilon, so that every time you pick a subgroup H in G, you have two options. Either your subgroup H has finite index, in which case, obviously, the growth rate of H is the growth rate of G, or there is a gap between the growth rate of H and the growth rate of G. So if you draw this on a line, so you have the possible growth rate of your group, subgroups. Here you have 0. Here the maximum growth rate is H of G. And you have a gap here of size epsilon. And in between those two things, so here you have all the finite index subgroup, obviously, but in between now, there is nothing else. All the other possible growth rates are in this. I should not use the same color. All the other possible growth rates are in this portion of the line, on the line. They are all here. So that's another nice statement, I think, that will use the same kind of techniques to be proved. So I will not discuss that one in detail because basically it's the same kind of proof that we need to somehow quantify more carefully, but I thought it was a good thing to state it. Questions? Okay, so if not, let's enter the core of the proof now. So as I told you, there are two directions in this statement. The first one is the easy one. If you know that the quotient is amenable, which is a priori a lot of information, then you can deduce that two numbers are the same. So I give you a proof when the subgroup is normal using Patterson-Sullivan measures. So I will not discuss that one more. I want to focus today and tomorrow on the harder direction, which is if you have two numbers, the growth rates, which are the same, which is a priori sort of weak information, then the quotient is amenable. And so here are the initial data that we will need. So I'm sorry, there is some technicality I will explain you why after. So everything I will state as for the easy direction on Tuesday, I will assume that the space X is cat minus 1. You can think also that X is just Hn or H2 even. That would be enough to follow the arguments. And you will not miss anything if you think in this way. And you have a group G which acts by isometry, and we will assume, of course, that the action would be strongly positively recurrent. So now, if you remember what we had done on Monday for the case of free groups, the idea was we had a certain operator, which was the adjacency matrix of a graph, and then we defined a twisted version of that operator. So we are going to do the same kind of twisted construction. So to be able to do a twist, we need a Hilbert space and a representation of a Hilbert space. So this is another part of the initial data. So we have a Hilbert space. Yeah, that would be nicer. Hilbert space. But now I need something else. I'll tell you right after why. I need to have a certain order, partial order of the Hilbert space. So to be able to speak of positive vectors. So you should not be afraid of that. This is very natural because all the Hilbert space we're going to consider essentially are the L2 function of something. And mostly will be the L2 function on the Schreier graph of the quotient. But for function, saying that a function is smaller than another, it's perfectly clear what it means. It means that point-wise, you have this inequality. And if you think of the scalar product that you have on your space L2, it has a very natural property that if you take the scalar product of two positive functions, then the outcome has to be a positive number. And this is what I mean by saying that the partial order is compatible with the Hilbert structure. So we have this Hilbert space, this order, which allows us to speak about positive vectors. And again, that's something very natural if you think in terms of a space of function, of L2 function. But now, next ingredient we need to do a twist, we need a representation. So we are going to fix a unitary representation, and we want this representation to preserve positive vectors. It should send positive vectors to positive vectors. Again, something also very natural if you think of square symbol functions. So if you have a group G that acts on the Y, that induces an action on the space L2 of Y, just by shifting the argument of your square symbol function. But if you started with a function which is positive, when you do that shift, the function still is positive at the end. So the representation you get here will be a positive representation in that sense. Okay, so that's the initial data I want. And now let's start to twist. So yesterday, I introduced the Poincaré theory of a group. And now we're going to do the same kind of thing, but adding a twist everywhere. So you can consider now this Poincaré theory, but you weight it by the representation that you started with. So I will try at each step to remind you where the different object lives, because maybe that's the most difficult part in this proof, is to remember what kind of creature you are manipulating at each step. So here, this series, provided it converges, it's just a bounded operator on your Hilbert space H. So actually, just before I speak about the convergence, just a side remark, we already saw some series like that. So if you remember the proof that I gave you for the easy direction, we were considering at some point a series of the form exponential minus s distant from O to GO times exponential chi of G, where chi was homomorphism. So you can think of this as being a representation. From G to GL1 R. Kind of easy or complicated way to write it down, but that's the same kind of idea. This representation is not a unitary representation, but that's the same kind of idea. We are considering a series, which is a Poincaré series, but where we added a twist by a certain representation. So here we are just much more brutal. Instead of using a representation, a one-dimensional representation, we use an infinite-dimensional representation. But why not? You will capture more information somehow in this way. Okay, so when you start working with those type of operators, you always need to precise what the convergence is, because there are hundreds of convergences in infinite dimensional space, and they are not the same, unfortunately. So here what we use is the strong operator topology, so which means that UN converge to a certain operator U if for every vector phi, UN of phi converge to U of phi for the standard norm on your Hilbert space. So this is what I mean by the strong operator topology. But actually, this is not the right way to think about it in my mind for the moment. So the idea that we are summing positive operators that sends positive vectors to positive vectors. And somehow when you sum positive operators, you have a phenomenon which is very, which is really a form of monotone convergence. So if you think of partial sum for this series, somehow that's an increasing sequence. And you want to say that when you have an increasing sequence, either it's bounded and it will converge, or it explodes. And so it turns out that here's the convergence. You can reformulate it in this way, that the series AS will converge if you can find a certain integer m such that for every finite, not certain integer, number m, so that for every finite subset of G, if you look at the partial sum for all the elements in S of exponential minus, oh, maybe S is not a good way, because there are two S's and my S are very similar. So let me call that finite subset F. So you have a finite subset F, such that every time you look at the partial sum exponential minus S distance from O to G O rho of G, you compute the operator norm of that thing. So this is again a bounded operator, so you can compute the operator norm, and this is at most M. So the sum of all partial series has uniformly, all partial series have uniformly bounded norm. And when you have this property, it turned out that the series converges for the strong operator topology. Otherwise, the norm explodes. So this is typically the kind of monotone convergence I was mentioning. So, and thanks to this behavior of monotone convergence, you can associate a critical exponent to your series. So the critical exponent would be some number that I wrote H rho, so that every time S is larger than H rho, the series converges, and every time S is smaller than H rho, the series diverges. Meaning that here we will be, when I say diverging here, it really means that the norm explodes. You don't have this kind of behavior of a bounded sequence of operator which is somehow turning around but never converging.
So rho of G is positive for every G is important for this definition to work. Is that right?
So yeah, to get this monotone convergence and to have this real threshold in terms of critical exponent, having an order on the Hilbert space and using a positive representation play a role. It plays an important role. And this is really, so there are some parts here and there when you can probably tweak the construction, but where this would not be needed. But I'll mention one point later where this is absolutely crucial.
Thank you. Thank you.
So in the same way that we assign to every group and every subgroup a critical exponent or growth rate, we can assign to a representation now a critical exponent, which is the critical exponent of this twisted Poincaré series. Okay, so how does it help for our problem, or how can we review our problem in this way? So remember now, the kind of representation we're interested in are regular representation on a coset space G mod H. So we fix the subgroup H of G, we have the L2 function on G mod H, and you get a regular representation, which, as I told you, is a positive representation. And the claim now is that the critical exponent of this twisted series is at most H of G and at least H of H. So if we think of our setting, we are interested in the case where H and G have the same growth rate. So what matters, what we matter is what's happening if rho and G have the same critical exponent. And it is really the situation we're going to investigate. So let me give you a few hints for the lemma. So I just rewrote the Poincaré series. I'm going to do all the computation in a very formal way. So if you want to do that carefully, you should go through partial sums, etc., etc. But that the nature of the proof is correct. So first inequality is, well, if I compute just the norm of AS, you just apply the triangle inequality. So basically, it's at most the sum of exponential minus S distant from O to GO, the norm of rho of G, but rho of G is just unitary representation, that its norm is 1. So this is just the Poincaré series of the group G. So which means that if this Poincaré series is convergent, then the series AS, the twisted series, converges as well. So that will give you that H rho is at most HG, just pure abstract nonsense. Okay? Now the other inequality, which is probably more interesting here, is the following. So imagine I define phi of U to be the direct, so that's a vector. I will define this as a vector in L2 of G mod H. And that would be the direct at UH, so on the coset UH. So it's 1 on the coset UH and 0 everywhere else. And now let me compute AS phi of E, so the direct at H, scalar phi of E. So that will be, well, let me write again, the sum of G of in G, exponential minus S distance from O to GO. And now I have rho of G, phi E, phi E. But this is also phi of G, phi E. That's just the definition of the unitary representation we're looking at. So it shifts the coset, so that we'll shift the direct mass at the coset. But this, what can we say about that? Well, this will be 1 if G is in H, and 0 otherwise. So all the direct masses in L2 of G mod H, they form an orthonormal basis of your space. So that means that my computation that I did here is just now the sum over all elements in H exponential minus S distance from O to GO. But now you recognize here the Poincaré series of the subgroup H, not of the group G. So if AS converges here, so you get a finite thing here, so that series here needs to converge as well. So which exactly means that now H rho is larger or equal than HH. And this is the other inequality. So more generally, here's an exercise you can do. If you compute the scalar product AS applied to phi E scalar with phi U, I hope I'm not mistaken. Maybe there are some inverses I messed up, but generally speaking, what you get is the Poincaré series not on H, but on the coset of H. So somehow inside this twisted series, you have all possible Poincaré series of all cosets, all H cosets of your group. And later we are going to somehow build from that a twisted measure. And one idea to keep in mind somehow that this twisted measure will package all possible Patterson-Sullivan measure of the group H and its coset. It will wrap up together all this kind of data. So that makes it a very rich object to manipulate, and that's, I guess, that's why we will be able to extract information from it. Okay, so is there any question on those twisted series?
Excuse me, I have one.
Sure.
I wanted to know if you consider a finite dimensional representation, the H row coming from the twisted Poincare series will give you the entropy, topological entropy with respect to which length, as in the ratio between the top and the bottom eigenvalue, or which one?
So say it again, you consider a finite dimensional representation?
Yes, and I do the same Poincare series, the twisted Poincare series.
Yes.
And I consider the H row. I was expecting that the H row might have an interpretation in terms of the eigenvalues of these eigen or singular values of the representation. So and I was wondering if it
yes,
had a.
I guess I'm not very comfortable with the question, because the trouble is, so to get a good notion of the critical exponent, you need this order on the Hilbert space.
Mm-hmm.
And when you start with a finite, you want a unitary representation with this positive. You want positive representation with finite dimension. I don't know many examples which are relevant in practice.
Okay. Sorry.
So I'll think a bit more about it, but there is a subtlety here with the definition of the critical exponent, because you need that positivity. And if you're finite dimensional, basically you're looking at, for instance, if you think of this example with the L2 of a coset space, you're looking at the L2 of a finite set. But then there is not much to say in this situation, I guess.
Okay. Thank you.
Does that make sense?
Yeah. Okay. Thanks.
Okay, so if there is no other question, let me now reformulate actually the statement we're really interested in. So as I told you, I told you, when the group G and the group H have the same exponential growth rate, the associated regular representation H row has the same growth rate as G. So we will focus in situation where the representation and the group has the same growth rate, the same critical exponent. Which means from now on, we can forget completely about the subgroup H. And the theorem we want to prove is the following. So you start with a Hilbert space which has this partial order. You take a positive unitary representation. And now I claim that the two statements are equivalent. The critical exponent H rho is the same as the growth rate of G. And rho almost has invariant vectors. So that will imply the hard direction, saying that if you start with the subgroup H, H and G have the same growth rate, will imply that the associated regular representation almost has invariant vector, which means that H is coinable in G. So you can do 2 implies 1 as an exercise. It's really not difficult. You just plug in almost invariant vectors into twisted series, and you will see that you can prove that the growth rate, the critical exponent in this situation has to be the same as the growth rate of G. The 2 implies 1 is not very difficult. So we will focus on the harder direction, which is 1 implied 2. Okay, so we have done a twisted Poincare series. Why not push further the analogy and do a twisted Patterson-Sullivan measure? So that would be a measure, hopefully on the boundary, that takes value in some space of operators. So let's have a first naive attempt, and we'll see where there's a little bug somewhere. So everything here will be very formal. One needs to justify a bit why it works, but I'll keep the more formal point of view because it makes it lighter to introduce. So let's do exactly the same thing we did for Patterson-Sullivan measure. So you consider the series, the Poincare series, where here the twisted one, where you add a Dirac mass at GO. You sum everything. So that gives you now a measure taking value in a set of bounded operators, and you add a renormalization exactly like for the Patterson-Sullivan measure. We were renormalized by the regular Poincare series. Here we're renormalized by the norm of the twisted Poincare series. So that's a measure from the compactification on X that takes value in the space of bounded operator of H. By the way, I forgot to write something. This is assuming that X is a point in a space X, and of course that little s is larger than H true, because you want the series to converge. So if you're familiar with the spectral theorem for self-adjoint operator, that will probably not surprise you to consider a measure which takes value into a space of operators. If you're a bit not at ease with this idea, so you can always think as those measures as being linear functional from the space of continuous function on X bar to the space of bounded operators on H. Actually, that's the way we wrote the paper. We entirely wrote the paper using linear functionals because that was a safe way to avoid saying some silly things about operator valued measure. But really, in our mind, we thought of this object as operator valued measure. So if you remember the construction we did for the Patterson-Sullivan measure, the idea was, okay, let's this exponent s here, let it tends to the critical exponent h rho, and we will make those measures converge to a certain measure supported on the boundary. So for the standard Patterson-Sullivan measure, we are very happy because the space of probability measure on a compact set is itself a compact set. So you can pass to subsequence that make sure that your family of measure indexed by S will converge. Here, there is a trouble. If you take operator valued measure, even if you normalize the way that those operators should, this total, the norm of the total mass somehow should be 1, this space is not compact, just because your operator space is not locally compact. So a priori, taking this limit as I wrote it here, it makes no sense. So we need a tool to bypass this difficulty. And this tool is basically a brutal hammer. It's called ultralimit. So I just rewrote here the basics about ultralimit. So you start with an ultrafilter, non-particle ultrafilter. So basically, it's a finitely additive probability measure on the subset of n that takes value either 0 or 1. And it has to be 0 on every finite subset. And then just for some vocabulary, so I use the notation of measure theory. So we will say that a property is true omega almost surely if the set of integers for which this property holds has measure 1 according to this ultrafilter. And then we say that if, a real sequence UN converges to a certain number L if the difference UN minus L is super small almost surely. So for every epsilon, the difference is as small, it is smaller than epsilon almost surely. So what's the good point of this definition is that every bounded sequence converges for this ultrafilter. So if you have never seen ultrafilters, don't be afraid of it. You just keep in mind the simple idea. This is a black box for extracting subsequences. When you work with real sequences, every time you have a bounded sequence, you can extract a converging bounded sequence. Here, you don't have to bother what subsequence you will extract. The ultrafilter does the job for you. And it shows one for every bounded sequence. So that's a very powerful tool. Actually, you need the axiom of choice to get the existence of such ultrafilters. But once you accept this powerful tool, it makes your life much, much easier. So how do we exploit that thing? So we are going to now introduce a construction which is the limit of Hilbert spaces, an ultra-limit of Hilbert spaces. So we start with a sequence of Hilbert space. And now I'm going to consider all the sequence of vectors in this Hilbert space which are bounded. So this is what I wrote in this way. And when you have a bounded sequence, since every bounded sequence converges according to your ultrafilter, you can define a pseudonorm on the sequence. So you say that the pseudonorm of the sequence is just a limit of the norm of the phi n. This is a number which always exists because we chose an ultrafilter. So now in this product, in this partial product here, which are all the sequence with pseudonorm 0. So that's a vector space. So if I want to turn my pseudonorm into honest norm, then what I just do is I consider the quotient, which I wrote h omega, that the quotient of this restricted product by the subspace of all sequence which has a pseudonorm 0. And now the pseudonorm on this quotient gives you a honest norm. And if you think being a Hilbert space, if you can reformulate that in terms of norm by just saying that the parallelogram identity holds. And if you write down the parallelogram identity in every space Hn, that's something which easily passes the limit. So you will get that this weird a priori space H omega will also satisfy the parallelogram identity, which means that this space is a Hilbert space. Yeah, I did not say, but those ultra limits, they are always complete somehow by construction. So I will think of this quotient space now as the limit of the space Hn. And that's why I will write limit omega of phi n for the image of the sequence phi n. So basically, you build a new Hilbert space by considering sequence of vectors. And it comes with a nice norm so that the resulting object is a Hilbert space itself. So once we have this definition, there is a lot of things we can elaborate on and reformulate. So for our purpose, what we're going to do is we have fixed the Hilbert space once for all. That the one for which we want to have almost invariant vector. And so we will take as a sequence of Hilbert space just a constant sequence, keep it easy. We say it's a constant sequence. And so this space H omega that we build, somehow you can think these are all possible sequence, bounded sequence of vectors, modulo certain equivalence relation. And it turned out that since you have an order on this on H, that gives you an order on H omega. Just this is pure abstract nonsense. You unwrap every single definition and you'll get that. And similarly, if you have a sequence of bounded operator on H, you can define a limit operator by the only relation you can expect. So your operator applied to a certain limit will be just the limit of your operator applied to phi n. So the only possible reasonable definition that you can write, that's the correct one. And that gives you a bound operator now on this limit space. So why do we do that? Well, because we're going to let the Poincare series, which are bounded operator, convert to something, but also because for the representation, in the same way, you can consider somehow the limit of the representation and get a representation from G to the unitary operators of H omega. And that representation is also a positive unitary representation. Just pure abstract nonsense. You write the definition of each object and you get it. So now a good exercise, if you want to get familiar with those kind of objects, those kind of limits, so is to prove that your original representation of rho almost has invariant vector, even only if rho omega has a non-zero invariant vector. So heuristically, the way you can think is H omega, we said that was a space of sequences. So if you have almost invariant vector, you have a sequence of vectors which are more and more invariant. But when you pass to the limit, because of the identification we do when we take the quotient, the limit representation will fix a vector, namely this limit of almost invariant vectors. And it goes in both directions. So what we really do, we will work in that space H omega, which is the limit of the constant sequence H, and consider that limit representation. And my goal now is to prove that rho omega has a non-zero invariant vector. Does that make sense? Yep. Okay, so yeah, I guess I'll give you the definition of the twisted Patterson-Sullivan measure, and probably we will stop here for today. I'll continue tomorrow. So now, second attempt to do a twisted Patterson-Sullivan measure. So again, I start with a basic definition. Well, for every point x in the space x, and for every s which is larger than the critical exponent of h rho, you build the Poincare series with a twisted one where you add a direct mass at every point in the orbit, and you rescale that by the norm of the total twisted Poincare series. And now let's fix a sequence Sn, which is always strictly bigger than h rho, and which converge to h rho. And I want to define now what is the limit of those measure AXS. So basically, you do the sort of only thing you can do is you will define, so if you take, sorry, I did not write some of the definitions. So if I take f to be a continuous function of x bar, so we want to do a convergent which is very like the weak star convergence. So what we will define by saying that the integral of f against this measure ax, that the limit of the integral of f against the measure I wrote above. So which means if you just write definition of the measure ax and sn, sorry, this is the limit of this thing. So just pause for a second so that we understand what kind of object we are manipulating. So AXSN, this stuff, that's a measure on X bar valued in the bounded operator of H. So if I just look at this integral, now this integral is a bounded operator on H, right? So if it is a bounded operator on H, now I can take the limit. So it's a sequence of bounded operator of H. So I can take the limit of that sequence, and what I get here now is a bounded operator on the limit Hilbert space H omega. So which means that what I have defined is a measure on X bar that takes its value in the space of bounded operator of H omega. Again, if you're not very comfortable with that, you can think this is just a certain linear functional from the space of continuous function on X bar to the space of bounded operator of H omega. And another way to reformulate is the exact same thing if you prefer not to think of operator valued measure. So that will be the main object we are going to study tomorrow, but let me just, maybe a small spoiler, but state the property we have from that. So first, that the measure will be supported on the boundary at infinity of x. So here, in the same way I cheated a bit for the standard Patterson-Sullivan measure, I cheated a bit here. I will explain you tomorrow why. There is a certain normalization. So if we look at the measure AO, we can take its total mass. So again, the mass here is an operator. So, and this operator has norm 1. So in the same way that the Patterson-Sullivan measure at O was a probability measure, here somehow the total mass of AO is an operator with norm 1. We also have some invariance when the group, oh, by the way, there is a typo here. When the group G acts on the measure, but that equivariance has a twist that comes from the representation. And finally, we have a similar conformality property. So here, what I wrote is very formal because I'm considering that there is a certain Radon-Nicodim derivative of two operator valued measure. There is no way such a thing should exist in general, but here we can prove that such a thing exists. And so the Radon-Nicodim derivative of AX with respect to AY, it should be an operator. And basically, this is the same kind of thing we have for standard Patterson-Sullivan measure. We have exponential minus h rho, the Boozman function at c between y and x, times here the identity operator. And we'll see tomorrow how we can exploit those kind of data in the same way we've done for the Patterson-Sullivan measure, using the shadows lemma and other stuff, to actually prove that when h rho is exactly the same as the growth rate of G, actually my twisted measure is absolutely continuous with respect to the standard Patterson-Sullivan measure. And that would be the key arguments to, at the end, get a non-zero invariant vector for rho omega. So I think I'll stop here so that we have a few minutes if you have questions, and I'll go on tomorrow.
All right, Remi, thanks for the lovely talk. I guess there were a few questions during the talk, but do we have further questions for Remi?
Yeah, one quick question. So this statement that you have here, that this measure is supported on the boundary. There, you're using this statistical what the positive recurrence, statistical quasi-convexity. Is that property that's being used here? Is that
no the property in those properties that I studied here are completely general. They are not using this strongly positively recurrent business. I will stress we use it exactly at a single point in the proof, and I will stress where we are going to use it. All the rest is very general.
Thank you. Thank you. Okay.
Any other questions? Okay. If not, then let's thank Remi again. And well, that's it for the day. And
well, thank you very much. Have a good day.
Bye.